You might want to turn off your audio. Hello, everyone, and thank you for joining us today. Welcome to Megger's Monthly Testing Tactics webinar series. Today's topic is PD testing in the life management of a cable. My name is Michael Fleischer. I'm the digital marketing specialist for Megger. I'll be acting as moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive 1 NIDA CTD and 1 PDH or 0.1 CEU for attending. You will receive this in an email within 2 business days of the webinar. That email will also include a copy of the PowerPoint presentation and a link to a video recording of the webinar if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation and they will be answered at the end of the webinar during the Q&A session. Our presenter today is Robert Probst, Megger Cable Products Manager. Also to assist with the question and answer section, we will have panelists joining us, Stephen Smalls, who is an applications engineer here at Megger. Okay, let's go ahead and get started. Thank you for joining us today, Robert.
Hello, everybody. So welcome to part 2 of our little cable testing and diagnostic series. So I just brought the screen back that you may recognize from the VLF webinar in December. So this was kind of the outline that we said we can do this year. So this one is done. If you want to go back to that recording, I will give a quick recap of that. And so we will move on, and today we will talk about the PD diagnostics, and then Stephen in December will do part 3 with the 10 delta diagnostics. In between, we will have some webinar for fault locating, and so this is pretty much the outline. So let's go from the VLF part to the PD part. So we will be talking about, as I said, a recap of all of that, some general comments, what is partial discharge testing, and then we will have a summary and talk a little bit more about the wave shapes. So I will bring this back as a general comment on testing and diagnostics. Pretty much, if you want to do effective asset management and condition-based maintenance, you kind of have to do all 3 of the tests that we introduced the last time. So you need the VLF test as your withstand test and as your reliability test, go, no go. For the aging condition of the extruded cables, you need the 10 delta test for the service age cables. And then there's this whole portion for PD testing. And as you can see, PD testing is also in the other 2 circles when it comes to being a tool for the condition assessment of aged cables and also being a tool for getting results during the acceptance testing of new installations. So keep this whole thing in mind. That's pretty much where PD, this is the general kind of application for PD testing. Then I'll bring this back just to recap on the general objective and motivation of what we're trying to achieve. So it's all about increasing the reliability. And last time in the webinar in December, we talked about the preventive part, the VLF testing part. Now we're talking about the predictive part, or let's say one portion of it, the PD part. And increasing reliability means you want to reduce your outage minutes, which directly affects your index numbers. And you also want to proactively check your whole cable population to be able to do a condition-based maintenance program. And that all feeds in technical information, so not guesswork or guesstimates or whatever, like technical information obtained by scientific methods to feed your asset management. And at the end of all of this is a cable replacement program, which is also under budget constraints And from then onwards, you can make educated decisions where to invest your money for an optimal allocation of your budget, of the limited money, because everybody knows everybody has limited money. If you would have an unlimited budget, none of that would matter because you just do whatever and you have the most pristine installation. But that's not reality. Even the largest utility companies have a budget restraint. So let's go to some introduction. So why are we even do PD testing? So first of all, it's never possible to avoid any damage during installation. It's simply not. You will always have some problems during laying. Mistakes can happen while people handling accessories, and at the end of the day, you have the aging. Existing installation these days, they are under a commercial pressure to be used longer than originally estimated or guessed. You want to exceed specifications and you want to maximize profit. So that puts an insane amount of pressure on the existing installations. And then obviously you also have a change in operations and regulations because everything goes towards safe and reliable operation. And that happens in distribution and transmission systems. And at the end of the day, this is what we're talking about. If you have a cable failure of one of these longer faults that take longer time to actually show themselves, then this is one of the results. You can see the splice body there near the connector, and you had a breakdown there that was due to a fault that, for instance, would have passed the VLF test because it takes so much time to actually show itself that a 1-hour test is not going to show it. Actually, no initial withstand test would show it, and then over time, it would come to this fault. Then I just want to make clear with these examples, I will talk a little bit what they mean here and what you see, that partial discharge is the #1 cause of severe cable failures within the installation. On the right, you see a transmission cable and end termination in a substation. And as you can see there is no outer skirts anymore. No housing or whatever. Like you don't see the polymer or the porcelain. In this case, it was porcelain, I believe, if I remember correctly. And that end termination had partial discharge in it, and it just exploded. And that was in an urban area. So that is, that was kind of like a big explosion, and everybody was just lucky that nobody got hit. Just people walking by, because even though it's kind of like you have fences and everything, but in an urban area, everything is dense and close. Then on the bottom, you see a gas insulated installation that exploded. And this is one failure, and it took them like months to clean up that failure in the first place before they could do a fairly straightforward joint repair or splice repair and put that transmission cable back into service. But you see all this the white byproduct, and this took like forever to clean up. Then on the top in the middle, you see typical medium voltage cable failure. Some splice blew up on an extruded cable, and on the left you see a pill cable failure. So this is what you get if you just keep the assets going without looking for partial discharge activity. So then in terms of a more abstract approach, what is the impact on the actual assets? Because the title of the webinar is the importance for the life cycle. So we want to look at the life cycle. So everybody is familiar with the typical bathtub curve. And you know, actually, I took this picture from a colleague. He found this kind of poetic picture to actually visualize this a little bit better. And there's the bathtub again, and you see, if you see this as a cradle to grave approach, initially, when you go from the infant stage, as you can see here, you have your typical initial problems. Then you have a long time nothing or very little happening, because that is the main period of operation. You will have some unexpected breakdowns. Most of them in the cable world will actually be induced from external sources. Let's say you have a cable installation and you have a severe lightning strike that could affect or cause a cable fault. So that would be one of these unexpected breakdowns. And then towards the end of life, and also already beginning in the middle, in the main time of operation, due to aging, due to conditions, due to the years of operation, contamination, harsh environmental conditions, you see the failure rate going up significantly. And now here the condition-based maintenance comes in big time, because with the right management of your resources and the right testing, you can substantially extend that time and maximize the maximum lifetime, so to speak, of your asset. And obviously everybody always has the question, so where is my cable here? And so the purpose of the testing is also to find out, at least initially, when you don't have set up a very sophisticated cable program, where is my cable here? I have a circuit, I don't know anything about it at this point in time. So where am I? I'm already like going up here in failure rate in the end of life towards the grave. Am I in the stable? Am I still suffering from some other problems? So just to establish the condition, it's very important to do testing as well. And then in terms of like the failure rate, or how you would want to invest your budget, I mean, there's various different investment strategies or models that you can follow, but mainly you want to invest as early as necessary and as late as possible. I repeat this, as late as possible and as early as necessary. So you want to find the sweet spot where you don't want to invest too much too early, but you don't want to wait too long to miss the point where a good and a fairly small investment would have made more sense. So, and to actually gather that information, testing will help you. In this case, PD testing predominantly. And then, of course, in the early fallout will be gross defects that will appear hopefully during acceptance testing, installation commissioning testing. Then here, this is just the area of maintenance. You will find hopefully just some smaller defects, and end of life will be when more failures will show themselves. And now to the point where the PD testing is most effective. So as you can see, 90%, and this is well-established statistics, there's multiple sources saying that, multiple even utilities have published figures like that, and they only vary very slightly in percentage. So some sources might put the big red chunk of that cake to 85%. Other sources would put it maybe to 92%, whatever, but 90 is a good number to go. So as you can see, the workmanship related issues dominate the failures of the various components of the cable. Then you have some issues with cable pulling, always happens, and transportation issues, including, by the way, I didn't write this here, but also including storage issues. Actually, when you sometimes see various utility yards, you can immediately tell if certain cables will cause you problems or not down the road, because there's a specific way of storing the cable drums. If you don't do it that way, let's say you put them upside down or you flip them over in the wrong way, that will cause sooner or later at least some mechanical deformation of the cable drums. So there is even a strongly preferred way of storing the drums before you do anything, before you go out, before you go into the trenches, pull the cables into the trenches. If you just store the drums in the wrong way in your yard, then you're setting yourself up for failure. Another thing is, when you store the drums, I can only, appeal to you with this, always put end caps on. Also, when you work in the trenches and a day of work is finished, make sure the ends of the cable, the exposed ends, are covered. So there's no chance that moisture can get into the cable as well, which in long time will also cause accelerated aging. And then you will see this sooner or later during the 10 delta testing. But that is like two things that you see very often: incorrect storage, not taking care of the exposed parts during installation. So moisture ingress, more moisture ingress that naturally would happen. And of course, transportation damage, incorrect lifting stuff, and wrong positioning on the trucks, cuts into the, my former colleague Jason, he always had an example, a picture which I don't have anymore, where a truck driver pretty much nailed the shipping bill on the cable itself, damaging the sheath and the main insulation right away. I mean, sometimes it's trivial like this. So as you can see, if we would have a test that can focus on the workmanship related issues, this would be awesome, because we would be able to find so many issues. And this is exactly what the PD testing is for. And then another thing which was interesting that was presented at the NITA conference last year, kind of where do the faults eventually, that the PD related faults occur. And as you can see, same thing, a tremendous amount of faults are related to the parts that humans touch. And this is just, how it always is. The moment humans come into play, errors are, reality, mistakes are made. And this is exactly what we see with cable installations as well. So then back to condition-based maintenance. So for the condition-based maintenance, again, you want to overall increase your reliability, and particularly for PD measurement. So what is really the benefit of this? Instead of just doing VLF testing, also putting PD measurement as the number 2 test there. So first of all, you are able to check and repair the assets, and back to here and to here. Now with this test, we can focus on the parts that are actually faulting or being faulted. And before anything seriously bad happens. And then obviously the result of the test should help us coming up with some sort of risk assessment. So we do not need to touch the power cables or replace the power cables before their, so to speak, technical life expectancy. So you don't want to run around and start replacing miles and miles of cables after 20 years. If it's not necessary, because you say, XLPE cables, you should get 40 years out of it. That's typically the nominal life expectancy for design, or maybe even 50 years. But for instance, I mean, it's expected that you're probably not getting the same life out of the extruded cables like we did out of the pill cables. And then this is pretty much the investment side of it. If you don't do anything, run to failure, like many people practiced over decades, you pretty much shortening the lifetime of your asset, because once the fault happens, then severe side effects show themselves. If you do a time-based maintenance, that's at least better than nothing, but it's very not very focused, not very intelligent, not very smart. Because just the installation year of a cable doesn't tell you anything about its condition. So when you go to condition-based maintenance, you get the optimal information to actually, as I said, optimally allocate the resources. So only the cables that really need the money actually get the money. And then in terms of what we know and what we have, as I titled that slide, overall in the cable, we have the cable and we have the accessories, period. And that's pretty much it. Now you know everything about there is to know about cables, kind of. So the cable itself is the main insulation. It's an unaltered part. It comes out of the cable manufacturer's plant, tested in a Faraday cage, up to 4 times operating voltage. I mean, the extruded cables, anything that is near 5 picocoulomb in terms of magnitude gets disqualified as a batch. So you should get these days a pristine type of, or pristine cable out of the factory. But then what happens, installation happens, you have to splice multiple drums together. If it's a longer cable, you have to put terminations on, you have to put splices in, and that's really the accessories. And the accessories have a very interesting feature. The accessories are all so-called layered interfaces. So you have multiple materials sharing surfaces against each other. Keep that in mind. This will become very important later on during the webinar, and we will circle back to that. And then in terms of methods, for all of these local issues, you can use PD testing, because PD testing can also localize the faults. And for the global degradation, the aging, you only have 10 delta. And just let me emphasize this again. These two tests are complementary. What the 10 delta test is showing you cannot be answered, or telling you cannot be answered by PD, and vice versa. So people who are always out there trying to replace one test with the other, they are not really getting the answers that they are looking for. Remember the first slide there, the circle. You need to ask all the questions to get all the answers. And then I stole this from a colleague of mine, so to speak, the next few slides, because in his diagnostic seminars, he always wants to get to the point that even complicated things can be explained in simple terms. So I left this example in. If you don't find it funny or whatever, blame the German humor. So here we go. So he said, okay, I want to define, or I want to explain what a truncated icosahedron is. And if you go, for instance, on Wikipedia and you get all the definitions of what it is, you know, in geometry, a truncated icosahedron is an Archimedean solid, you know, with 13 convex, isogonal, non-prismatic solids. You have 12 regular pentagonal faces, 20 regular hexagonal faces, 60 vertices, 90 edges, blah, blah, blah. If you're not like mathematically inclined or you like that stuff, this is kind of like gibberish to you. And down here, even in chemistry, yeah, that's the fullerene C60 molecule, right? So everybody knows what that means. And so this is the structure, for instance, of that molecule, or of what we just talked about, that truncated icosahedron. And now a very straightforward simplification. I say every pentagon I make black, I color black, and every hexagon I color white, and then I get this. And everybody knows that. Even Americans know that, okay? So that is a soccer ball, or as it correctly is called, a football. And that is kind of the easy way to explain these things. So you can say, oh yeah, this is a soccer ball, or if you're an engineer or whatever, a PhD, then you say it's a truncated icosahedron. So what I want to show you is the definition of partial discharge is quite eloquent and worthy in the standard. And here I have to say, I want to mention that the IEC standard is the gold standard. Even though IEEE is following up now and tries to define that, the IEC standard is there since forever, and it is very substantial. It is very thick. It is an exhaustive comment on how to do the signal processing. Then there's something for the experts, if anybody is listening in, the weighing function, where you actually, you know, kind of determine or integrate over the whole frequency spectrum that you recorded. Everything is explained there in very deep technical details, and all the test circuits are defined there. And this has been, as I said, the gold standard. And it says, for instance, this is just a chunk of the explanation. A partial discharge is a small electric spark that occurs at an insulation defect of whatever nature, but it does not completely bridge the insulation from high voltage to ground. These defects may be just cavities. It might be inside accessories, as I said, the interfacial condition, and then along surfaces, which would be on the terminations. And again, partial discharge, the presence of partial discharge pretty much tells you it is a non-reversible destruction of solid or even mixed insulation material. And the unit is 1 coulomb, or better, picocoulomb or nanocoulomb, which is like 10 to the minus 12 or 10 to the minus 9 less. So that means 1 billionth or 1 trillionth less of 1 coulomb. Actually, I'm by training, I'm a high voltage engineer. 1 coulomb is an insanely large charge. So if you charge a sphere in free space up to 1 coulomb, that's already some substantial charge. So in the cable world, we're talking picocoulomb. So 12 zeros after the decimal point, or nanocoulomb, 9 zeros after the decimal point. And again, say it easy, use the soccer ball terminology. So you can say, what are partial discharge exactly in terms of practical operations? You know, you're in the field, what does it all mean? It's a release of energy at an unwanted and unforeseen location by means of design, okay? So somebody designed the cable and the termination, and the PD occurs in the spot where it should not be PD present at that location. That's pretty much what that means. It damages and, even more important, decomposes surrounding material. It leads to a reduction in life expectancy. It will lead and initiate to the breakdown of the insulation sooner or later. It's tracking there, it's getting there. The end result is the entire failure of the asset, which can be catastrophic. If you think a little bit outside of cable, if you have internal PD in the transformers, and a transformer just fails, that's a dramatic loss for the utility, especially these days with less redundancy built into the commercial operation. So typically, back in the days, people had spare transformers right there, and they were able in a fairly short amount of time to install a new transformer. Typically, that is not the case anymore. All these spare transformers have been kind of eliminated for commercial reasons. And very important, I just want to point this out. It's kind of duh, but I just want to say it. Of course, PD are measurable. If they weren't measurable, we would be in big trouble, but they're measurable, so you can do something with the physics of them. And again, the result would be something like this. You have a tracking fault there, and sooner or later, you will have a flash over and a failure of the asset. So you can call PD in the soccer ball language, it's the predator of insulation, okay? It hunts insulation down, like this guy. Remember this guy? Okay, so what is the precondition of that? So to start a PD, you need sufficient electric stress, dielectric stress, which is directly related, keep that also in mind, to the peak voltage, okay? So you start an ionization process, you need what's called a starting electron, wherever that comes from, background radiation, cosmic radiation, whatever, you get this, and it starts an avalanche mechanism. For the experts out there, it starts as a Townsend discharge, so you have to meet the threshold for the Townsend parameter that the avalanche is be able to feed itself, and then causes that micro discharge. And so in a nutshell, what can cause partial discharge in the accessory? Well, of course, improper installation, even aging, manufacturing defects, even though that is kind of getting less and less because the quality procedures and processes are improving. It can be due to environmental third-party damage. Somebody just hits the cable. And again, if you measure partial discharge, you are able, if you do it correctly, to get an early warning and do something before it's too late. So how do we measure PD? Just in short, there's two ways. There's conventional and non-conventional, and that is really the official terminology. So everything that is considered conventional testing always, everywhere, follows IEC 6270, the test circuits outlined in IEC 270. The conventional measurements always have a coupling capacitor, and only in conventional testing we are allowed to talk about picocoulombs because the test circuit is calibrated and the data processing and the signal detection is all done as outlined by IEC 6270. As soon as you leave that ground, you're not doing internationally accepted conventional testing anymore. So if you cut your frequency spectrum short, you're not integrating over the entire frequency spectrum anymore. You're calculating the weighing function differently from your pulses that you detect. Any of that, and you're leaving the realm of IEC 6270 testing. And then the opposite, obviously, is anything that is not conventional is obviously non-conventional testing, which is anything that has to do with transient earth voltages, high frequency CTs, ultrasonic sound, if you use capacitive sensors, corona cameras, temperature related issues with thermal cameras, all of that is non-conventional, and most online methods are per definition also non-conventional because they are monitoring methods. You cannot calibrate the circuit because you rely on operating voltage, so it's kind of a warning system. You gain yourself a little bit time just before the catastrophic failure to take action, but you don't really see the condition coming because you cannot vary system voltage to 1.7 times or something like that to see if there's a condition coming up and growing. So the best way actually to actually see this is partial discharge testing, is kind of the non-intrusive kind of test, or minimal intrusive, you can call it. And typically when you use a non-continuous waveform, as we will talk in a second, it's also considered non-destructive. And at the end of the day, you want to find out what circuits to prioritize. And we talked about this. This is just a little bit more elaborate. You get the presentation, so we don't have to talk here. You can read up on these things. And then typical things that you see, the irregularities in the insulation material is you can have the classic thing, voids, imperfections, protrusions. All of these things will cause partial discharge and electrical treeing at one point. At one point, water treeing will cause electrical treeing, even though those electrical trees are of a very different magnitude than real PD. So typically, it's very difficult, borderline impossible to really catch those. And then what's the consequence of PD? So the problem here is if you do a VLF test and a VLF test only, and that has been established for years. This is no news. Some people, they run around and they try to say, oh, VLF testing is not finding all the faults. Well, that was clear pretty much almost from the beginning, a few years into the VLF testing. Once pretty much everybody, in this case in Europe, adapted VLF testing and got their reliability numbers up, they hit another wall, so to speak, and they wanted to know more. They needed to know more. And that was the transition from preventive maintenance to predictive maintenance with some condition-based aspects to that. So it was never like that VLF can find all the failures or all the growing failures, especially not a new installation when there is no water trees that you can create electrical trees. Gross defects it will find, no problem. But if a cable passes at 3 U knot VLF test, then you know if you throw the switch, it's not going to blow up. But is there a condition that will show itself in 8 months, 12 months, 36 months? It might be the case. So, and this is where, you know, you should do more than just VLF testing. And the consequence of that is also in the cable, which can be dramatic. You have a heat evolution, as it's called, because of the heating in the insulation from the discharge. You have this byproducts that are eroding the solids or even the pilk, or causing the tracking in the pilk and all the vaporization, the local vaporization of oil. And you create radicals, which create even more problems with ozone and NOx that contributes to the corrosion even more. And then you get things like this, you know, tracking, corrosion, and then on the left, heat problems. So in the insulation, specifically in solid dielectric cables, what do you have there? You have the weak spots, you have the isolated particles, cracks. All of these things are actually sources of PD. And actually, you have to make a complement to today's cable manufacturers, let's say Nexans or even Prysmian. Today's cables are really, really good. Modern XLPE cables should not have these things anymore. And to be very honest, if you go around in Europe, Middle East, Southeast Asia, you know, they all have similar levels of cable, and they purchase from a few suppliers. And typically modern cables do not have this from the factory. So that should be not really a major concern anymore to have these localized, isolated weak spots. It's more of a question, terminations and splices, where you have the layered interfaces. And just really quick, in PILC, you have the paper layers, which are there for mechanical stability, and the oil is really the insulation medium, or the mass, when you say paper mass cables. So you can have these carbonized tracks along the paper. I had a little picture of that before, where you saw the paper and all the tracking there and the treeing. You can have multiple other problems with the PIL cables, water intrusion, lead corrosion, all of that. That's one thing why 10 delta is not such a great test for the PIL cables, because you have additional aging mechanism and not just the water treeing like in extruded cables. So, and then, you know, because that is always a question that we get, what does TDR have to do with PD analysis? Well, the main method of localization and the only real reliable method that produces good results is the so-called traveling wave method, or the pulse propagation method, which is kind of you using TDR analysis to find out where the location of the PD source was. And the way it works is, as you can see in this little picture, you have a PD source somewhere, and 50% of the energy is in shape of a pulse, is traveling to the detector directly. The other 50% is traveling to the cable end, being reflected, and then traveling to the detector. And if you do an analysis of these events happening in the time domain, you can actually calculate the location of the PD. And just to illustrate this even more, so, and just one more comment before I go to the next slide. It's not actually TDR traces that you see there. It's not radar traces. It's similar, but it's not the same as you would hook up a radar, let's say, you know, a Teleflex or something, to a cable and do a TDR measurement, because the PD source is somewhere in the cable. So if you want to think about this, yeah, it's kind of like TDR. Always keep in mind, in terms of PD analysis, it is as if you would connect the TDR somewhere in the middle or somewhere else in the cable, and not at your near end. That's the big difference. And that is kind of, it changes the way, the paradigm of how to look at these traces. Because if you look at them with the mindset, oh, this is exactly like a TDR trace, then it will be confusing. So we have these three cases. The cases from just the slide before is in the middle. So the 50% that went to the left, to the near end, to the detector, is right there and is being shown as that kind of reflection, that blue one there. And then the red one comes later because the second reflection, because it goes all the way to the cable end and comes back. And then there is a time difference, a delta t, and then that allows you to calculate the distance of the source from the detector. Now, if we have a PD fault, and I hope you can see the animation that is starting soon, at the near end, close to the detector, this is going to happen. First reflection, and we're in the time domain, remember that. Reflection at the end. Tick-tock, tick-tock, tick-tock. Arrival at the detector, and you have your second reflection. Now, as you can see, I tried to, or in this animation, it was attempted to show also what happens to these pulses, which is very important for the software algorithm that discriminates the pulses. Cables are capacitive objects, capacitive assets with a strong low frequency filter behavior. So the cables tend to filter away high frequency components in these pulses. So you have two effects. You have attenuation, which is the loss of energy, the reduction in magnitude of the pulse, where the longer it runs along the cable, and you have dispersion, which is the widening of the pulse itself. So if you want to be a little bit colorful with the description, you know, soccer ball language, you can call this the pancake effect. You're taking a very nice pulse of defined frequency spectrum and defined magnitude, height, and you're turning it into a pancake when it comes back out of the cable, once it goes in the cable and comes back out. So it's flattened and it's widened. So the flattening is the dampening or the attenuation, and the widening is the dispersion, the loss of high frequency components. And the algorithms that try to find out, is that really a PD pulse or is it something else? They also look at attenuation and dispersion as additional calculation parameters to find out what's going on. And then case 3 on the bottom, you have a PD source close to the end of the cable. So as you can see, the first reflection arrives, and then shortly after, the second reflection arrives. So you have the paradox situation here that the reflection, I mean, if you don't really think about it, you might jump to wrong conclusions. And actually here, if you have a PD source close to you, the pulses are far apart. If you have a PD source far away from you, the two reflections are fairly close together because you're measuring really the time difference between first and second reflection. So it's a relative measurement. So just really quickly about phased resolve partial discharge. I don't want to talk about this too much. There is something that's called phased resolve partial discharge patterns, which gives you the location or a graphic indication of a PD pulse resolved over one period of the waveform. So it looks something like this. And there's a lot of theory behind and a lot of theoretical and laboratory testing that went on how to identify the different patterns. I just gave you 3 examples really quick that were recorded in a laboratory in this case. How do these different cloud patterns form? So all of these things, these reds and grays and oranges, that is one single dot. And you recorded all of these dots and resolved over the phase angle, you get these cloud patterns. On cables, this is not really too useful. On other assets, let's say motors and generators, it's very useful because there the asset is, or the device is built in a way that the traveling method is useless in a generator winding or something. But the phase resolve patterns will tell you a lot where it happens, end winding or somewhere else in the stator or on the rotor, whatever you're testing. And so the phase resolve patterns in the motor testing business have a very good application there. And now just something about the intensity. So what you want to see during PD testing, you're measuring various things, various key parameters, and the most key parameter is the partial discharge inception voltage, PDIV, followed by the PD mapping, the intensity at U0 that comes out of IEC. The discrimination of the criticality should be done at operating voltage U0. And then there's PD extinction voltage. You know, you trigger an event. When does this event stop again? Or does it stop at all? You know, these things. That is kind of like the relationship. There is a so-called hysteresis between the two, so a connection between IV and EV, which is kind of phenomenological, so it's kind of tested, but it cannot really be derived from a set of equations, at least not very precisely. Rule of thumb, what you see in the fields, PD EV extinction voltage is typically between 70% and 90% of the inception voltage. So it's less, and it can be 10% less up to 30% less. That's the extreme numbers that you see. So rule of thumb, you can say 80% of IV typically, with exceptions. So it's just, you know, an idea. It's not exact. So you start the event, or the partial discharge is being ignited, and it goes out at 80% less. So then from the practical point of view, how do you do the test? Well, first of all, you connect your setup, which is fairly straightforward with a few hiccups and pitfalls that I will be addressing at the end. So first of all, you connect your coupler. The first thing that you do is you have to calibrate the circuit. So you put a calibrator on that injects a known charge, a known pulse of a known frequency spectrum with a known magnitude. And then you pretty much record this kind of trace. And then you save that trace, and the software will use this as its gold standard for the measurement to discriminate against. So any pulse that runs into will be judged against that calibration pulse that you recorded earlier on. And then you do a background noise measurement. So in the field, obviously, you can never reach factory conditions. That's absolutely impossible. You can sometimes be lucky, and if you make a good ground connection, you know, a proper grounding scheme, you don't create large ground loops, antennas, and everything. You keep the connection from the coupler with the coupling capacitor very short to the actual connection point. All of these things help. And you will get you can sometimes achieve a very low background noise. If you're in a very high noise environment, well, it is what it is. And that is pretty much your minimum threshold, or your floor that you cannot go below. If you have a condition that is below the background noise, no chance of finding that in the field, because of, well, that's the nature of field testing. You have background noise. And then you start at a certain voltage, and you, in steps, increase that, not too many measurements, not too few. You not always have to be there according to IEC, because that's the criticality, really, the threshold for the criticality. On serviced age cables, you go up to 1.7. On new cables, you go up to 2.2. There is no excuse for anybody, not for the manufacturer of the connection technology, the connector technology, not for the splicer himself, to not be able to make a PD-free splice up to 2U0 these days. That's very well possible. And on new installation, nothing less should be accepted, if I were you, so to speak. On serviced age cables, this 1.7 seems random. It is actually not really random. If you think about the three-phase system, what is the most common failure? It's the single-phase fault, which is the ground fault. So one phase suffers a ground fault. What happens to the other two phases? Their line to neutral voltage gets elevated to the line to line level, which is √3 higher than the operating voltage. So it's 1.7. √3 is 1.732 and many more digits. And so you say 1.7. So if you do a test up to this, that means you tested for the ground fault condition. That's also the case, remember, back at the VLF testing when we talked about practical test practice. When you have serviced age cables and you do not want to do 3U0 for the withstand test, you should never go less than 1.7, because that's your ground fault test value level. So that means and again, I repeat myself, if a cable, a very old serviced age cable, passes a VLF test 1.7 times U0, that doesn't mean it's good. It just means, okay, I'm okay for the next ground fault, and I can proceed, and I'm probably not better than just 1 year or something. So I won't get this 2 to 3 years reliability that you got from Dortmund and Malaysia, the field studies. Then during the test, you define by this step procedure the inception voltage and then the extinction voltage in the software. And then I just want to show you some example again. So you have some change, this transition from a water tree to an electrical tree inside the solid insulation, and this is just one type of partial discharge, and that will keep tracking and tracking and tracking until you have an insulation failure. So this is predominantly caught by VLF testing though, because the magnitude of these is so low and the growth rate is also fairly high, that to do a PD test just at the verge of, oh hey, I'm able to measure electrical trees, very statistically very unlikely and also very difficult, because if the background noise is kind of 80 picocoulomb or 100, these things are in the 20, 30, 40 or something picocoulomb. So typically not what you can see with a standard issue PD test. That is something why you do VLF testing. You rake these things out with the VLF test. And then in the splice assembly faults, that's what actually causes all these troubles. Misalignments, cuts, sharp edges, improper installed Faraday cages, you know, the mesh, all of these things, conductive impureness. I brought some examples. I will go through them fairly quickly. So here it's like one-sided sanding. You see this will cause a void. You know, you will have a gas in solid dielectric discharge that will give you problems. This will be prone to a tracking fault. You will have this slip off of the peeling tool and causing problems. Then an unforeseen step that should not be there. It causes a sharp edge for the electric field, where the field lights get compressed, as I said, the Townsend mechanism, and then you get your partial discharge. Then you have this conductive impurity. They didn't polish it properly, and the graphite film is conductive. This will cause you partial discharge. And then here a cut into, which will cause, and then also an incorrect alignment, which will cause the also a hotspot for partial discharge right there, because you will have a small cavity. So how do you prevent this? Well, you do a good job, actually, and you make sure that your splicers are educated very well on the different splicing technologies. See, there's a saying in Europe, specifically in Germany, the wealth of the utilities is underground. Because if you do the installation properly and you have a very good cable from the beginning, and the jacket is undamaged, so you did your sheath fault testing as well, then you have a printing press, kind of, because the asset is there, minimum maintenance, especially on the latest generation tree retardant XLPE in terms of water treeing. And so it's actually just making you money as a utility, because little maintenance and little failure rates. Cables have a very, very low failure rate compared to overhead lines per year per 100 kilometer, or per year per 60 miles, as these numbers are typically expressed. Observe the bending radius. Classic mistake. They bend the cable too much, and on one side it's compressed, on the other one it's stretched. You get voids. All of these things. Just do a proper installation, and you will have a very nice PD-free life. And then what voltage waveforms are available from your test set? And this is actually very important. This is kind of like the most important thing. You have 3 voltages these days that you can do PD testing with. The 50-60 hertz is pretty much non-applicable, because a long cable is a huge capacitor. If you charge this at 50 hertz or 60 hertz, you need an insane amount of reactive power to supply that, you quickly end up with like size of an 18-wheeler or building size, which is okay for type testing facilities and cable manufacturers because they have a building available. You know, Kima, the big test lab in Arnhem, they have a whole high voltage lab with huge AC sources when they do these type tests for the 500 kV cables or whatever, because they can afford it. It's in stationary, it's not mobile equipment, so you can dedicate a building for that and do it at 50 hertz or whatever, or 60 hertz, and that's fine. Or you do it with resonance test sets, which can also grow very big in the field. It's typically these 18-wheelers where you bring an inductor and you find a good frequency where an energy transfer happens, the resonance between the inductance and the capacitance of the cable. That is pretty much the technology pioneered in the 1990s for the transmission cables. But this is all not really applicable, and most people, if they can avoid these things, they try to, because it's costly, it's large, it's a lot of effort to do. So the first voltage waveform that was established as a diagnostics waveform in transmission and now migrated to distribution is dampened AC, DAC, or oscillating wave voltage. It's a decaying dampening voltage, starting at a peak, and then after 200 milliseconds or something, the shot is gone. It's non-continuous, therefore minimal intrusive, and typically non-destructive. You charge the cable, you close a switch, the inductor in the test set resonates with the capacitance, but then you keep the switch closed so it dampens out based on the losses of the system. And that voltage there's secret papers on that, the first to be established to get the same results as true 50 and 60 hertz testing. Inception voltages are comparable, activity is comparable, magnitudes are comparable. So that is the go-to technology for diagnostics PD testing. And the waveform looks like this, well-defined in IEC, also well-defined in IEEE now. They have a separate chapter on damped AC in the IEEE 400, and the typical frequency range is 30 to 500, sometimes 20 to 500, but 30 to 500 is kind of the resonance test sets. So again, you charge up with DC, you close the discharge switch, you keep it closed, and it rings out and it's gone after a few hundred milliseconds. So then we have two other waveforms which are based on VLF technology. And this is the only reason why this whole topic becomes a little bit convoluted. The problem really is that originally PD testing was not done with VLF, and then the market kind of went to this or demanded it or asked the manufacturers, and then as a second development, the VLF waveforms came into play. And there's two. Again, I want to make sure, call back to the webinar in December. Remember, the first one, the original, was the cosine rectangular, invented again by Eckhard Lehfeld at HDW in Kiel, HDW in Kiel. And that was the cosine rectangular VLF. And that has very interesting features. I will show you a picture later on if you haven't seen the other webinar. So that is one of the VLF waveforms. And then there's the sinusoidal VLF, the 0.1 hertz sinusoidal. And both VLF waveforms are also suitable kind of from a theoretical point of view because their reactive power demand is so much less. So it's kind of damped AC, you know. You need a fairly small DC source to charge the cable and then cause the resonance. So you don't need a lot of power in the field to charge the cable to do the testing. And it's the same with VLF because of the frequency, the reactive component, the apparent power that you need to charge the cable is so much less. Now, the sine wave VLF is much different in terms of waveform than the cosine rectangular. So this is the cosine rectangular. You have a dwell time and then a swing over, which is the polarity reversal. So the overall, obviously, it's 0.1 hertz. So it's 5 seconds positive, 5 seconds negative. And the transition happens in milliseconds. It actually happens at the slope, at the steepness of the power frequency, which is very important. And then you have the actual slope technology, as we call it. The difference here is not the waveform, the difference is the parameters. And let me just make one thing clear, also call back again to the other webinar. When you do a VLF withstand test, both waveforms, 0.1 Hertz sinusoidal and 0.1 Hertz cosine rectangular, are equivalent and getting equivalent results if you apply the IEC testing conditions, which means everything is scaled in RMS values, which means that the peak of the sinusoidal is 41% higher than the cosine rectangular, because then the RMS value is the same. Why is that important? Why does VLF has to be seen as RMS? Because the tree growth, the growth of the electrical trees, is a function of the frequency, that's well known, but mainly a function of the energy. And the energy you pump into a system is directly related to the RMS. Now, the inception of partial discharge, you want to do partial discharge testing and duplicate the same physics as 50 Hertz power frequency and damped AC. The inception voltage is also a function of the frequency, as was established and is well known for many years now, but is a function of the peak voltages. So that's the reason why when you go to slope operation, let's say on one of our test sets, the slope is corrected by a factor of √2 to give you the right peak stress to initiate the same physics for the PD measurement. So there's a distinct difference between the VLF withstand testing and using cosine rectangular for the partial discharge testing. And that's perfectly fine. That's established. And the second thing, which is, I mentioned it the last time in the webinar as well, the cosine rectangular was never intended to be used for diagnostics testing. The customers came to us and said, hey, can we use that? And we said, we don't know. So there was 4 major studies conducted. And what pretty much was done was that the test results were compared to damped AC. And since damped AC was already proven to be comparable to power frequency, then the logic conclusion is cosine rectangular is comparable to power frequency. So you get the same partial discharge inception voltages, and you get the same, in principle, the same activity. The difference is typically because you have this higher voltage stress in the insulation and a continuous wave shape compared to the non-continuous wave shape damped AC, that the magnitude of the PDs are higher. So if you test a cable, everything in the mapping will be the same between damped AC and cosine rectangular, except that the picocoulomb values will be higher as in the for the cosine rectangular for the slope. So yeah, I just explained this. It's the diagnostic way of applying cosine rectangular. And then you have the sinusoidal, which is generated completely different by power electronics, AC to DC, DC to AC converters, and every quarter cycle the heat has to be dissipated in a resistor to be able to reverse the polarity. Now remember, it's so much slower, like power frequency, 500, 600 times slower, 1,000 times you can say, because of the amount of polarity reversals. And that is also true in the zero crossing. Over the entire waveform, it is much, much slower than obviously power frequency, and it doesn't have this quick transition in the milliseconds that slope has. So that's a very distinct difference, which makes all the difference in the real world. So because I told you, inception voltage is a function of the frequency with a low gradient, a low rate of change of voltage, you are not reproducing the correct physics. And this is what we see in the field left and right, that the sinusoidal test results are typically, on average, not comparable to 50 Hertz slope or damped AC. And again, this is the reason. The DUDT, the gradient of the voltage over the entire waveform, specifically in the zero crossing. And I spelled it out a little bit better. Some of you might know this because it's like a slide that we use pretty often. So here you see a blue block, which is the power frequency. It's so many polarity reversals, it appears to be solid. It's actually not. And it's one full VLF cycle. So you can see the dampened AC is already quite different. The cosine rectangular is quite different. And you see the orange is the 0.1 Hertz sinusoidal. And if you zoom in, you get this situation. And as you can see, the gradient is so much different with the sinusoidal. And that is kind of the main reason why that waveform is quite different from the other VLF and from the established diagnostics waveforms. Now, really quickly, in the last 5 minutes, some case studies. So I put some together here. You see the company is called Enro, and it's a very small system, actually. I pulled down some numbers from their annual report, and they have like a 26 megawatt peak and 27 kilometers cable at all. So very, I mean, this is tiny, right? So why would they do PD testing, right? What, is that justified? Well, look on the right. Enro is feeding, it's south of Berlin, is feeding an industrial park that has all kinds of global players in them. So you have a production related facility of Toyota, you have Mercedes, you have, actually this is not in here, you have ATU Aero, so the supplier for the airplane industry. You have Kraus, you have Gestamp, all of these big players, these mid-sized but globally operational players, and you have some corporates there. So if you have a cable outage in Enro, the red phone is calling you immediately. I mean, it goes out and the red phone is not standing still, kind of. So they have a very big interest of keeping the lights on. And they had quite a story, actually, to tell here. They had this cable, and I don't want to go too much into the details. This is one of the examples we really dissect in the seminars as well and in the long training sessions. So you have a 20 kV XLPE cable, so 12 kV is U0, that's the operating voltage, sent the conductor to concentric, and installed 2004 XLPE. And they had some problems after they did some testing, and they called in a contractor. He found some faulty joints, then they repeated it, and for some reason, even though they, tried to repair it, they got similar results again, and now they weren't sure what to do. They brought in another contractor that used sinusoidal technology. This guy didn't get any of the results from before, from the contractor that used DAC. So now they were even more confused. And so what to do? So we were in the area, and they asked us, hey, please bring your test van. That test van has a test system installed that's called TDM4540, and it has all three waveforms. It can do sinusoidal and 10 delta. It can do cosine rectangular / slope, and it can do damped AC. And they wanted to see the difference. They asked us to do a comparable measurement. And this is the measurement. Up to U0, you get the results with damped AC and with slope. And you can see very similar to what the contractor measured. And the sinusoidal was kind of quiet, nothing there. Then you go up to 1.7 and you see a whole lot more coming out of that XLPE cable. Now, sinusoidal is measuring something as well, but look at the count up there, look at the histogram, if you can read this. That's the amount of discharges measured, and see these bars there, they're for the three phases, L1, L2, and L3, and you see the count is pretty much a few 10, while the other two waveforms, specifically slope, they have a few hundred counts there. And if you go on, then it goes into the thousands. And then down there, you see the cloud patterns that form. Look at the magnitude. Sinusoidal, 250, 500 in that area. And the other two waveforms are in the thousands, so alarming. And again, at operating voltage, the condition was already present, and sinusoidal just measures it now. And here again is the inception voltage as a comparison. So keep in mind, again, this is why I spelled it out like this. The IV is the critical parameter aside from judging the criticality at U0, okay? Because partial discharge at U0 means it's always there. And then you have a big problem. And so that means if you would have based your assessment on solely the sinusoidal results, you would have assessed it too good to be too positive. You would have walked away and you would have said, yeah, there's something going on, maybe inception here at 1.3. I come back in a few years or something, whatever your risk management is. You elevated it probably from green to yellow, so you monitor it closely, but you're not in an alarmed state or something. Like you don't say, oh, this is a critical condition. While the other two waveforms tell you there is failure imminent, and you have substantial problems in the splices. Now the side story starts. So they tried to locate where that joint is, and remember they were confused because they saw at least at one location the same pattern after they thought they repaired. Well, what happened was they cut out the wrong joint. And as we found out, with some TDR-based location method, they went to the wrong location. See, they didn't go to the one at 650 meters. They went to a different one. When you see these results popping up, there's this additional, I don't know if you see the mouse pointer, there's this additional condition now coming up. And so pretty much they cut out the wrong splice, and when they respliced it, they did a poor job. So not only do they still have the critical joint in there, or the failing joint, they also created another weak spot now by insufficient quality of workmanship. So that is kind of like, then they send it in to this company, Innogy. I just wanted to show you the latest results. That is what I got back from our field test engineer that keeps track of that case. And he said, hey, look at this, they found this. So problems, definitely workmanship issues. And then they cut it open. So you see the analysis, and you see it should be a flush interface kind of, and you have all voids all over the place, and an incorrect positioning of the stress cone or the stress element. And so you were entrapping a gas inside a void surrounded by solid material, and that caused partial discharges. So as I said, the latest news is they cut out the wrong joint as the first attempt. And now they're contemplating the next action. The big takeaway for Endro here is they will keep doing the damped AC testing because the sinusoidal did not give them good results. Then we have another company. I pulled some numbers. Enso in Saxony, one of the federal states. It's also one of our factories is close to them as well. So this is how this sample ended up on our desk. They have approximately 1 billion euros annual revenue. So that's, I don't know, at the moment, $1.2 billion dollars or whatever, roughly 500,000 customers in some bigger cities and in some rural areas. And so they have this cable, typical German, typical European cable, some pilk left from the big push for XLPE, but not pure XLPE. And again, we used the test van. We connected it to the cabinet. Here you see, get an idea of the test circuit. You have the source, the coupler, and then from the cable drum there or from the coupler there to the cable. And on the very left, you have the digital, the software and the signal processing and everything. And this is what we got. Similar results. Look at the count at operating voltage, 2 events for sinusoidal at 60 or 80 picocoulomb. And the other two waveforms, they go haywire already. Really, they say, oh, 2,000 picocoulomb and whatnot. Now, please, also 1.7, then it gets more severe. Again, compare the intensity, a few 10 counts, a few 10 events on sinusoidal, a few hundred on the other two, and 250 picocoulomb compared to 4,000, 5,000, or 2,500 for damped AC. Keep in mind, PILC is involved, so the results will always be kind of different because pretty much any PILC cable these days in Europe will have partial discharge on them because they're so old. The way, or the fact that they can tolerate that is lies in the fact that the insulation medium is a fluid and it's not a solid, so it's not deteriorating that quickly and that harshly because it's partially self-healing. It's to a certain extent a fluid is self-healing. So here what you just see is that a comparison what results you get with the different waveforms. Most of the activity here was in the PILC, so it was deemed to be, well, we monitor it, but we don't go DEFCON 1 or something like that, you know. And so the summary, again, based on the sinusoidal, it would have been too positive. At least Enzo knew we have to take a look at these transitional splices and all of the other things that we saw. So decision making is really important. It can only be correct at good data. And then the last example before we're coming to an end here, finally, we had a van tour scheduled for that system, and again, it has that all-in-one test system in it. And we went to the racetrack in Vienna, and they had prepared like a demo for us. So it was a customer that challenged us, and they had prepared a cable drum, and they put 3 man-made faults in there. Okay, and just excuse me. So 3 man-made faults, and they said, okay, there you go. And they invited other manufacturers. So technically our competitors were there as well. So it was a big, you know, event, and customers were there and everything, other people, and everybody wanted to see, everybody was kind of, you know, eager to see what the outcome was. So what happened was we tested with all 3 waveforms again, and we tried to find these weak spots. And what we did was some of the results that we found. And what you can actually see here is that we did a 3-phase test, obviously, that a comparison between damped AC, slope, and sine, again, you almost see no red, but you see a lot of blue and yellow, which in this case, we color-coded this to have a simultaneously comparison of the results in one trace. And you can see up to operating voltage, slope and damped AC see something, and even 1.3 times you not sinusoidal is silent, and only later on at higher voltage, it starts to pick up. Now, very important here, so here's the PD mapping again. So the slope catches it first at operating voltage already. The dampened AC follows in the similar pattern, similar, you know, clouds and magnitude, and then the sinus follows. And the big takeaway message here is, which made us a little bit, you know, proud. None of our competitors could find any of the weak spots, and we found 2 out of the 3 that they prepared for us. So we scored 2 out of 3. The customer was very happy, and the competitors that used only sinusoidal technology they were not able to see any of those. And then just the last bit that was like a big thing that made big waves back in the days already. Unfortunately, that became a little bit forgotten, this case study. The biggest utility company in Europe, E.ON, at that point, they split the company recently. So it's not this one huge company anymore, but, you know, a few years ago, it was 120 billion euros annual revenue and over 35 million customers in various countries of the EU. And they challenged this whole thing again. They said, we want to know what the gradient of the voltage has in terms of influence. So they invited 2 manufacturers without knowing that they were tested and investigated. and they had a particular troublesome splice, and they let them test at the splice. So the 50 hertz AC test set was able to charge the cable, was a huge test set, and it came up with the assessment, hey, that splice is critical, man. You know, you have PD at operating voltage, so do something. And the sinusoidal guy said, oh, there's nothing really going on. We are PD free up to 2 U0 and even 2.5 U0. And E.ON published these results without knowing, and then it caused a little bit of an earthquake in the industry, because you see that was done already 2004. So the takeaway message here is, because of the insufficient rate of change of voltage, you get a relationship between the voltage waveforms like this. 50 hertz, not practical for field testing. Damped AC as the gold standard. Slope, the cosine rectangular diagnostics, comparable to damped AC, and the sinusoidal problems with inception voltage, amount of counts like the intensity and the magnitude. And these are some more pictures. You see the tracking. It's not the best picture, but you see the surface is getting damaged. So action was required. That was the takeaway message from that comparison. And so what E.ON pretty much said is, hey, these things are so in the layered interfaces. Again, circling back to the accessories. Accessories are layered interfaces. In the cable, there's little chance that you have any impurities these days, so your focus should be on the accessories. And these layered interfaces, because its surface discharges are very sensitive to the gradient, to the frequency for incepting. And there's numerous scientific publications. A very nice one from fairly recently is Jäferberg and Edin from the University of Stockholm in Sweden, and they pretty much said, hey, at low du dt, the PD extinguish, and this is pretty much relating to what you see in the field with the 0.1 hertz sinusoidal being so slow. And then it's just another thing is that the activity that you get, you see the amount of count, and what you see, that this is recorded in the laboratory. So you see the surface discharges are so sensitive to the gradient. And then that is a fairly recent publication that is also interesting, because it tells you, well, in these refractive field control elements in the joints, it's really important to have something that is comparable to power frequency to be able to get a correct assessment under operating voltage condition. And I believe this is the conclusion of everything. So I just, made up some statements here, which were, shown in the slides before. So damped AC is the go-to method for the past 20 years now, not just 10 years, 20 years now. For high voltage cable, it's very established there, and for medium voltage cable, there is two VLF waveforms. Remember that. There is the cosine rectangular, or slope in terms of diagnostics, and the sinusoidal. CR, cosine rectangular, has to be proven to be comparable to damped AC and power frequency. So if you use that, you get comparable results on average. So there, I just want to make this clear. There's cases where the three waveforms get the same measurements, but more often than not, sinusoidal has performance problems and has problems showing a real representation of what's going on in the cable. And now one more last comment. So why would you ever use slope if damped AC seems to be the gold standard? Well, the latest, hottest thing in the industry is moving away from just VLF testing, going to monitored withstand testing, which means you do a fully compliant VLF test because you have to do this. It's your withstand test for the commissioning. But you record a diagnostics indicator, and that is for new cable installations, preferably the PD. And now circling back to what you just saw, if really 90% of the failures happening in accessories, and if accessories are layered interfaces, and if you do not have to worry so much about the local isolated weak spots, and you should worry about the surface discharges and the tracking and everything in the layered interfaces, you should combine the VLF testing with PD testing, and then you can use slope because it's a fully standard compliant waveform giving you the pressure test, the withstand test, and it duplicates the correct physics that will give you the right activity in the splices if there is any. So for the commissioning testing, PD plus cosine rectangular is the preferred withstand test, monitored withstand test. And this pretty much concludes everything, so I give back to Michael.
Thanks, Robert. At this time, the presentation portion of the webinar is officially ended. All right, so now we'll take about 30 minutes to answer any questions that we have. If you have any questions, please submit them now in the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can request a demo or a quote on any Megger products. A copy of the presentation, along with a link to the video recording of the webinar, will be emailed to everyone in about a week. You can also view video recordings of previous webinars on our website at us.megger.com/webinars and register for next month's webinar, Battery Maintenance Load Testing, Standard Requirements and Recommended Practices. The presenter will be Volny Naranjo, who is a Senior Applications Engineer. Now let's get to your questions. So first off, we have a question. What is unique about Megger's method of testing for PD, Robert?
Oh, what is unique? A very specific question. I mean, unique is pretty much that we're the only, I would say, undogmatic manufacturer. Like we have all three waveforms, and we will never tell you kind of, you know, you only should use this method and you only should use the other method. You should always use the appropriate method for the problem at hand, for the problem in front of you. If you want to measure 10 delta, use a sinusoidal test set or the sinusoidal waveform. If you want to do monitored withstand testing with accompanied PD trending, use slope. If you want to do pure diagnostics testing of the partial discharges, use damped AC. So the uniqueness is kind of that we have all the waveforms and we have test sets that can produce all the waveforms, namely the TDS systems and the TDM systems. So we have waveforms that are comparable to power frequency, and we would always recommend you to use the right thing for the right problem.
All right, excellent. Next question is, are PDs always occurring in the cable? And if so, at what point should you consider replacing the cable?
Okay, this is one of the most common questions, you know, that you run into. So if we think about a cable, let me just jump back here. I think you should still be able to see the screen.
Yep.
One moment. When you think about the cable, okay, so there is PD kind of everywhere in the power industry if you want to. Like transformers can have PD, terminations can have PD, some form of PD is corona, you know, PD in gases, external PD on transmission lines. So PD is nothing unusual, nothing specific to the cable. However, since the cable is a unique type of asset, it's distributed, it has a length, it has a spatial distribution compared to the other assets. Let's say a transformer is a very located, compact, stationary object. You know, it's there and it's there. So it's not stretching for 5 kilometers or 10 miles or something. So, when PD occur in cable, that is a whole different animal than when it occurs in some other substation assets. I mean, we have solutions as well for monitoring medium voltage switchgear. That would be the product called PD Scan. And for high voltage transmission environments let's say the high voltage end terminations or something like that. There's the UHF detector, so the non-conventional measurements. But that is more like substation monitoring or substation testing. Like on cable, that is a whole different animal in terms of PD. And PD in cable itself, as I said, you would have to have what's called a field intensity related fault, which is the voids, which are very rarely seen these days. The manufacturing quality of Nexans, Südkabel in Germany, Prysmian, General Cable, well, that's Prysmian now. Prysmian purchased them. I mean, at least in Europe, I can say we rarely see these defects anymore. I'm not entirely sure if it's the same over here. I'm hearing different things, so I'm not willing to make a statement on that. I just know from Europe that we rarely see any of these manufacturing-related defects anymore, because you also have to think about the type test in the factory. They have a Faraday cage, a shielded room, or a double shielded room to get any background noise out of the measurement. And then the type testing procedure is typically going up to 4 times U0, 4 times operating voltage, and any batch that comes out of the extruder that is more than 5 picocoulomb or approaching 5 picocoulomb gets disqualified. And then they will look at the process. Hey, what's going on? We have contamination, we have problems. So yes, the PD occur mainly in the accessories if they are there, because that's also what humans touch, right? That's the workmanship related thing.
All right, and our next question is, what test frequency do you recommend, and how often should this test be performed?
So we as Megger cannot establish obviously any kind of procedure or standard in terms of, this is what you should do just for liability reasons. What we have is, which we typically also show and talk about and discuss in the seminars and all these educational things that are longer than a webinar. We have recommendations from utilities. So utilities shared with us what they are doing for risk assessment and what they are doing for decision making. And I can tell you it's very different from utility to utility. Like one typical thing I can say about extruded cables is new cable, when you test it up to 2 times U0, PD free. Serviced age cable, you test up to 1.7, and then you say a very common threshold for people to take action and to be very concerned is 1,000 picocoulomb in the splices, for instance. We have utilities that are way stricter, and we have utilities that are a little bit more lenient on that. But on average is that at the end of the day, as a company, you have to come up with your own plan on how often to test, what the thresholds are, what actions to take. I can tell you, up to a few months or years ago, Singapore was the most strict utility when it came to that. They saw a splice that was 500 picocoulomb, they would immediately cut it out, because it's a city-state, a city country, 6 million plus people. The power needs to be on, okay, no risk taken. I think recently I heard because of the success they had with their rigorous testing program, they loosened up a little bit. There was a big study recently in Germany, and a few utility companies participated, and they had numbers like 1,000 picocoulomb, something like that. And then it's also up to your risk management. If you're just establishing PD testing and diagnostics, you probably test a little bit more frequently than when you have established everything and you just repeat routine stuff, It really depends on your risk assessment matrix, but anything that is severe in count, intensity, and inception voltage, you should schedule for immediate action or for repetition. For instance, seasonal influences are very big as well. So if you test in winter, or in the wet season and you come back in the dry season, results might already be different, because if you have water in a joint, water, hinders partial discharge to come out because of the failure of inception, because of the fluid. So you might get different results, right? So it really depends on what the individual company comes up with, what they want to tolerate. And some people, they say, I come back if I have a non-critical green assessment in my risk assessment matrix. I can come back after 5 years or 6 years or whatever, and it typically is harmonized with the VLF repetition. Then it's harmonized typically with the 10 delta, you know, when people start doing 10 delta once the cable is serviced age, because 10 delta is a useless test on a new cable. So, and you try to come up with a schedule for the outages where you can benefit. You take one outage, you do multiple things, and you harmonize that. But if you have a more prone problem, you probably say, hey, I come back in 6 months or a year and I retest, and I see if I have degradation. And if something that is already critical, PD at operating voltage, for instance, or PD above operating voltage and extinction voltage below operating voltage, you might want to come back more often or take action or something like that. So that would be a good approach.
Thank you. The next question is, as far as I know, obviously they know, I don't, PD trend value is important and not PD absolute value. So how can we test cable through PD absolute value?
The absolute value is quite important because you calibrate the circuit, and that's the whole trick with this IEC circuit, that it is the only calibrated PD measurement. Because if you have PD that is below the background noise, then it's very well important that you're not measuring that, because that magnitude is hidden in the background noise. If you get anything substantial, from our experience, is that any defect that is really there tracking damaging splices or a termination internally, that will show in the hundreds of picocoulombs or more, even in the thousands. And I mean, if you get a measurement that goes into the nanocoulomb and higher, then this is very well different from if I just measure 100 picocoulomb in the splice. And so both is important. The trending, when you say trending in meaning coming back every so often and watching what you're measuring, and then the absolute value there is also of importance, because if you go to a circuit today, you take the measurement, you save the data, and you come back 2 years from now, and the magnitudes have changed, that is your one of the parameters that you judge the degradation by, because your magnitude went higher. So it's a combination of both. Look at the calibrated absolute magnitude to get a feeling what's going on, because magnitude is not the same as magnitude, as you could see in the case studies. And then see by trending the cloud patterns, if a new activity pops up that was not there before, what is going on in the cable. So it's pretty much, it is kind of feeding the asset management. You don't want to take blind immediate action and spread your money if that cable could hold out another 2 or 3 years. That's what you're trying to find out with recording these values. You try to take action as early as necessary, but as late as possible. And on cables, you do the mapping, you get the mapping, you get the activity, you look at the count. That's what I do after I looked at the magnitude. So you look at how many events were triggered, and then you say, okay, where's the weak point, and then you just compare it to the next measurement.
So Robert, this is a good opportunity. This questioner asked about what is the IEEE or any other standard for this test? Does the standard specify the PD value for service cable and new cable, service stage versus new? And I know we talk about IEC often, but given most of the audience is IEEE, it's a good opportunity to make this clarification.
So an IEEE, there is a separate chapter on that, which is IEEE 400.4 for the damped AC. And IEEE has not established absolute values yet. these numbers that I'm telling you is the stuff that we got back from the utility companies and that what we see in the field. And I intentionally did not put up a table in this presentation because then I'm afraid people run around and say, oh, Megger said. It's really, we have this stuff, we have it from at least 3-4 very different utilities, and they're all similar and they're all dissimilar to a certain extent. And in the standard itself, in IEEE, there is not an absolute value established, but we know from experience that a few hundred picocoulomb is typically what you see, and then it goes up into the thousands. So I expect with a revision of the standards that some mentioning of a range or a band of these magnitudes will at least happen. I hope so. So yeah, IEEE would be IEEE 400.4 would be the damped AC chapter. And again, I really hope that there's a sort of harmonization and recognition going on that IEC has done all the groundwork already and with all the measurement circuits and how you integrate the signals and everything. So I hope that shows up in IEEE in future revisions in the same way.
Right, well, excellent. Next question is, what is your take on MV cable rejuvenation? Does it really work as a long-term fix, or am I buying a few months when the cable replacement is really needed?
Okay, so I assume that you had some visit from our friends from Novinium. So yeah, Novinium is doing, for instance, these cable injections. And you have to say, from a chemical point of view, it works to a certain extent. The problem with this is, like, solid dielectric cable, when you change their dielectric properties, you see big changes in the what you measure during the test, the condition-based testing. So what cable rejuvenation means, they inject a silicone fluid that jellifies and solidifies the insulation again and tries to bring back some of the dielectric strength. Now, this curing process can take quite a bit, months to years. You typically say at least a year, sometimes even more. And in that time, I'm telling you, if you measure the 10 delta during that time, you go out of your mind, because you see numbers like insane changes, weekly changes, because there's a chemical process going on in that cable. So from our experience or from our take, since we're not direct competitors, it has some value to it. It is obviously not the perfect tool. I mean, the dielectric strength is another thing. It comes back over time. The compounds change every so often. They have these cryptic codes for naming these fluids, and it has some value. For some cable, it's not really applicable. Let's say, for instance, for bare concentric, you typically would not do that. And so for unjacketed cable. And the other thing, what utilities typically do is, because you get mixed reviews. Some utilities like it, some say, yeah, it's okay. Some don't like it at all because the results are mixed. But what they typically also try to do is measure the corrosion of the neutral, and if it's more than 50%, then they typically also don't do injection. That's from what I heard from some utilities. So it has some value, but it's obviously like nothing in the world. It's not the silver bullet that can do everything.
It's a very practical question, Robert. Length of cable.
Yes.
Is there an end, a maximum?
Yes, there is, but that also depends on the cable construction, because remember, it's TDR-like localization. So if you have a cable with a high attenuation, the typical pulse doesn't go very far. So then what you have to do is you have to calibrate with higher pulses. So instead of calibrating typically with 1 nanocoulomb, that's what you do, 1,000 pico. That's a very common calibration setting. You calibrate maybe with 10 nano or 50 nano or 100 nano, so 100,000 picocoulomb, to get a pulse energetic enough that it can reach the far end and come back. At one point, if the cable gets too long, you have to measure from both sides, or you have to measure the cable. You have to cut the cable in the middle and measure like both ends. I mean, every method has its limits, but that kind of localization based on TDR and traveling wave and this reflection analysis is already better than anything else in terms of you do a real measurement, you can see really far into the cable, and depending on the cable, it's between, I would say, rule of thumb, on average, 2, 3, sometimes 5 kilometers. Sometimes 10, depends.
Another practical workmanship question. In performing PD testing on existing service cables, is it necessary to remove the connections from both ends? Some clients are skeptical of removing terminations. How would you perform this kind of testing if the cable cannot be removed from the equipment, such as transformer or switchgear?
Well, see, this is a bit of a problem because all the test standards, especially the cable test standards, they want the cable to be isolated from anything else. So you do not have to take off the terminations, like off the cable. You don't necessarily have to remove the terminations, but you should, if possible, if any way possible, disconnect from the switchgear or from the transformer. And I mean, in the medium voltage world, this is typically fairly achievable. If it's not achievable, you will have the problem that you see reflections and you might get influence from the asset that is connected to the cable. So whenever possible, you should try to have just the cable. Also for VLF testing, I mean, I would not do this when you have like other equipment connected if it's not like necessary. I mean, there's some systems in the US, these network systems, and some of these network operators, they cannot isolate the transformers. Well, then the transformer creates a giant high capacitance cable because there's no way of isolating. So then, you know, everything has to take the VLF voltage in those branch downtown networks. But if you can isolate the cable specifically also in URD and all of these applications, you should try to do that. And one more word on that, because Stephen said a practical question. Stay away from using dielectric materials, isolating materials to shield nearby objects. Let's say you are in a confined space switchgear and you disconnect the termination and you bend it away to get some clearance. Do not put rubber mats over these other parts because that will make it worse. Why? Rule of thumb is if you have a sphere around your disconnected termination of 8 inches, 20 centimeters, the influence of the other grounded objects is minimized and you should not get too much corona. But if you put in a rubber mat or any kind of like barriers or whatever, what happens from a high voltage point of view is that the so-called dielectric flow hits you and gets you because the electric field lines, since there is a material in the presence of the electric field that has a permittivity dissimilar to air. So I repeat that, okay? So any solid material, when it is a straightforward dielectric isolating material, has an epsilon relative, a permittivity, a dielectric constant. That constant describes how the field lines behave compared to air or vacuum. Air and vacuum, air has approximately 1. So if you have a material like XLPE and its permittivity is 2.3, that means the field lines are 2.3 times more intense than in air. So if you have a rubber mat or anything made out of a material that has a significant epsilon, like significant permittivity, you create a hotspot for the field lines there because the field lines are compressed into the dielectric material and you create more corona. I know it sounds kind of counterintuitive, but the best thing is always bend the cable a little bit back and just have it suspended in air, and your sphere of 20 centimeters around so you don't get much influence. That's really the best way to have the cable. If you have anything else, you might get corona, or the other asset, if it's still connected, is in there. If it is what it is, well, then you cannot help it. But then you should be aware of that you measure other things as well, or you might measure other things as well, getting reflections from the impedance mismatches and all of these things. So the ideal is to have the cable by itself.
The next question, I'm going to modify it slightly. It's a comparison between online and offline measurement practices. And maybe we can inject some of the technology differences between this.
Yeah, so online and offline, I didn't include the slides here because I decided it was already long enough, and I know I went 15 minutes over at least. So what you can pretty much say is online versus offline. Online is a tool for substation monitoring mainly, to monitor concentrated assets under system operating conditions, vibration levels, voltage levels, all these things like under operating conditions, but you cannot vary the system voltage. That means you cannot measure the condition of the assets, of the assets, of the insulation, because for that you need to vary the voltage. You need to be able to go 1 U0 and beyond to see if there is something coming up and to see what it's like. I mean, try it the next time, okay? Call dispatcher and say, hey, I'm here, in the middle of whatever, I am in a residential neighborhood, and I have this 15 kV cable. Can you raise the operating voltage to 35 kV, please, so I can see what it does at elevated voltage level? But be prepared for a rant with a lot of curse words from the dispatcher. So you cannot vary the system voltage, so you're limited to this. So online is kind of a warning tool. It gives you an alert, an alarm, once a certain condition shows itself, and it gives you a last chance to react and take action and prevent a catastrophic failure. But you cannot see it coming, and you cannot keep track of the condition because you cannot vary the voltage. While on the other side, offline testing, that is not really for monitoring. That is, the asset has to be de-energized in a scheduled outage, and then you have full control over all the parameters of the test, and then you can really find out the condition. So that is the big difference. The one is really a substation monitoring tool. The other one, offline PD testing, is the cable tool. As I said, different animals. I hope that answers that question. Oh, and one more thing, monitoring, online testing, again, non-conventional with these distributed sensors and everything, it's not calibrated. So the offline circuit is calibrated, so you really get an idea of the apparent charge.
And a related question to this online versus offline, differences between a UHF PDD versus a PD scan. So in talking about our products in this case, but the methods behind that, a PD scan is really a little device, a small device for the medium voltage switchgear. That's predominantly the application. It has various accessories, test sensors, transient earth voltage sensors. It has the acoustic parabolic. It has the capacitive sensors and all of these things, these sets. And that is mainly for medium voltage switchgear, fairly low cost to keep it attractive. The UHF uses UHF-like antenna or radio frequency, and that is a spectrum analyzer really. And that is for the higher voltage environments, high voltage substations and end terminations and all of these things. So there's a distinct application difference, PD scan for medium voltage switchgear, and the UHF, as we call it, or the method is called UHF detection, that is for your substations and transmission substations.
Oh, thanks. So when we're testing on a cable spool, do we need to pre-lay the cable on the floor prior to testing for DAC tests, or could it be done while the cable's on the spool itself? Additionally, can we also use that to find a bad pilot in the cable, in addition to the LG and LL faults?
Okay, so when you say pilot, I assume you mean the fiber optic in this case, something like that. You have to be careful with this when you say taking it off of the spool. IEEE knows 3 tests for the VLF test. There is an installation test, there is an acceptance test, and then there is a maintenance test. The installation test is supposed to be done the last time before you touch the cables and joint it or splice it and terminate it. This is to make sure that the mechanical laying did not cause any gross defects. I mean, if you want to, you can do a PD test, but you won't see much. You might see corona a lot from your connection point because it's not yet installed with accessories. But in the cable itself, on the PD test, you don't expect to see much. It doesn't have water trees, so no electrical trees from the aging, and it should not have anything in there. What you really want to do is you want to do the PD test as an acceptance test when the cable is fully installed, and you want to combine it with a VLF test as an acceptance test. So I would say to do a partial discharge test on a pure cable before it's in the trench and before you have it spliced together and terminated, it's not really telling you much, and it's twice the effort, because you want to repeat that when the cable is ready to be energized anyhow. So you might as well do all the workmanship and then see, because again, go back to that diagram here, right? This is what you're after with the PD test, localization of the workmanship, the quality of the workmanship. And again, most of the stuff by physics is happening in the accessories. So it's beneficial to have the accessories on and the cable ready to go for acceptance testing to then do the PD test. I would not really say it's much use to do it just on the reel or something like that, because you have to kind of terminate it or make a good connection to avoid seeing corona and everything, and then still you have the problem. You need very low background noise, and you probably don't see anything, at least very, very little.
All right, and so we only have time for one more question.
That's fine.
So we're just going to go with, what is the recommended frequency for the test for a maintenance point of view? Like, how often do they need to be running these tests?
Again, I think we had this question before. It depends really on your asset management program and the way you see what is critical and what is non-critical and everything. But typically, you say at least 5 years if it's non-critical. And more often, if it is, let's say, if you have a good test result, but it's a critical feeder, you might want to go every 2 or 3 years because it's a critical feeder. So it really depends on your risk assessment matrix that you come up with. Let's do one more.
Okay, sure.
There was a question related to an assessment criteria, specifically focusing on PDEV versus IV. The importance of one measurement over the other.
Well, the important measurement is for the inception voltage. It should always be above U naught. That is one of the main things where you say that splits or severs how many, or critical is at operating voltage and below, and per definition not so critical is above operating voltage. So, and then it comes on top. Okay, how many counts? What's the event count? How many pulses do you get? What is the inception voltage really? Is it closer to U naught? Is it far away from U naught? Again, on new cable, be rigorous. 2 U naught PD free is achievable and should be done, and should be like the thing to judge it. Because a new cable, there's nothing in the cable. The splicers should do a good job. You don't want to touch this cable for another 5 or maybe even 10 years. And you don't want to, so you want to have a good cable. So during acceptance testing on new cable, 2 U naught PD free should be doable. On service age cables, just monitor it. Once you get activity at 1.7 and then 1.5, 1.3, keep it measuring every so often. And again, accelerate based also on the importance of the feeder. An unimportant cable does not have to be tested that often than an important cable. And even an uncritical important cable should be tested much more often then maybe a medium critical cable that is not so important. Again, you want to maximize on time of the asset and find the sweet spot when to go in with your money and work some miracles.
Well, excellent.
Okay.
Yeah, that seems like a great spot to end. I'm sorry that's all the time we have. If we didn't get to your question today, we'll try and follow up with you offline in the next couple of weeks. Also, feel free to reach out to us offline as well. Thank you all for attending. Please remember to answer the survey. The survey also includes a feel free to request a quote or a demo if you're interested. Thank you all again for attending and have a great weekend.